Hi everyone, my name is Eduardo Uchoa. I'm a full professor at the Universidade Federal Fluminense in Brazil and an international chair in France. And 3 days ago, I read something that really caught my attention. It was about a new system, AlphaEvolve, and I watched several YouTube videos on it, and I decided that I have something interesting to say about this Alpha Evolve. Let's see what are my impressions about this Alpha Evolve. So this is a Gemini-powered covert agent for designing advanced algorithms devised by Google. Okay? And the idea is that it can be used for a scientific and algorithm discovery. And in particular, this AlphaEvolve, it could find a new algorithm for multiplying two 4x4 matrices. And this is something that was very impressive. And what are my views? So the AlphaEvolve was announced May 14th and sparked a lot of reactions. And unhappily to me, they include a lot of hype and misconceptions. So I ranked my opinions by what I consider to be hype by the degree of exaggeration. So the first thing that I disagree is that matrix multiplication was revolutionized. I do not agree with that. Second point, artificial intelligence can already discover highly original and creative algorithms. I do not at least fully agree with that. I have serious restrictions on that. And there are more serious claims that are being done. The first is that the profession of mathematician is doomed, and this system may even trigger a kind of technology singularity. Is, does it make sense? But okay, so we have here videos saying that this is a wide breakthrough in math after 56 years, and very big revolution on matrix multiplication, and so that AI can it's outsmarting human coders and mathematicians. Here we can see Isaac Newton crying because there's no place for mathematicians in the new world. And yes, this will trigger the technology singularities. So we are in a point in history where technology will explode. And okay, does it make sense? What this system has of so extraordinary to allow people to make such wild claims? Let's have a look at it. So, what is the big breakthrough obtained by this system? So it improved the number of multiplications required for multiplying two 4x4 matrices of complex numbers. Okay, this is true for sure. But in my view, the practical impact of this improvement is marginal. And more important than this new multiplication algorithms lacks the true originality and mathematical creativity that is being claimed. But on the other hand, I agree that it represents a big achievement, but a big achievement on optimization. Let's see about my point. I will have to be a bit technical in the next slides so I can really present my point. So, what is matrix multiplication? So the standard algorithm for multiplying two n by n matrices, we need n to the cube scalar multiplications. Okay, so the 2 by 2, we have matrix A, matrix B, and we have this very simple formula that we learned in high school. And this formula requires 8 multiplications. Okay. And then in 1969, Strassen realized that you can multiply two by two matrix only using 7 multiplications. And how he did that? So he first computed 7 products. So those 7 products that are written here from M1 to M7, okay? And then he combined, he added and subtracted those products and could arrive at the correct result, the correct multiplication of I times B. Okay, great. But who wants to multiply 2 by 2 matrices? But he made something very important. He realized, well, first, that this works. Why this works? Let's have a look at M2 and M4. If you sum the two, you have exactly A21 times B11 plus A22 times B21, which is the correct product for this element of matrix C. So you can check for all the 4 elements of matrix C that this is the correct answer. And but he realized that this can be done recursively. So if you have a matrix, 2 matrices of large n, you can partition the matrix into 4, each matrix into 4, and you can apply the same scheme recursively. So you multiply M1, in this case M1 is a matrix, so you compute the product of A11 plus A22 times B11 plus B22 to compute M1, and then you do the same and you arrive at the correct product. Okay, and by doing this, you arrive at an algorithm that performs not n cube multiplications, but n to the log of 7 in basis 2, which is about n to the 2.8. Okay, so this is very important. So this algorithm is widely used in practice because matrix multiplication is a very basic problem in computer science, in optimization, in machine learning, and whatever. So this is a very important algorithm. So people try to improve this algorithm to multiply matrices using even less multiplications, and they found better algorithms. Okay, and we have here a sequence of improvements, and now we know that it's possible to multiply 2 matrices in n power to 2.37. But in practice, all those algorithms are not really practical. And why? Because they are quite complicated and they have large constants that are hidden in the big O notation, and so they're not really used. Okay, and as a note, we may say that today the standard, the naive n cube multiplication can be surprisingly effective because in modern hardware like GPU, you can multiply, you can do a lot of parallelism, and this very simple algorithm is better suited for GPU. So sometimes the standard multiplication is faster than Strassen. Okay. Okay. And how to improve Strassen algorithm? So it was known, in fact, of course, Strassen already knew this, that it's a matter of solving a combinatorial optimization problem. So what's the idea? The idea is that you should consider you should try to find the best possible way of multiplying 2 matrices n times n for a fixed value of n, for a very small fixed value of n, and then you can do the same reason, you can obtain better recursions. And this is a combinatorial optimization problem. So it corresponds to find what we call the minimum number of tensors that sum to the desired result. So what are the tensors? So Strassen found his scheme by hand, okay, but today Strassen could have used a computer to find this scheme. And the idea is that each possible product and its application in matrix C defines what we call a tensor. So for example, M2 corresponds to the following tensor. So in red, we have that we are taking elements A21 and A22 from matrix I. This is why the coefficients in the tensor are 1, 1. In blue, we have the coefficients that are taken in that product from matrix B. So only B11 coefficient is 1. And in green, we have how the product is applied in C. So M2 is applied in to compute C21, and it's applied to compute C22, but it's applied with coefficient -1, so it's subtracted. So this tensor defines not only the product M2, but how that product is applied to obtain the final result. And what is the optimization problem that we need to solve to rediscover Strassen algorithm? So how many tensors do we have? In this case, each tensor has 12 components, and they can assume only 3 values. So 0, they are not used. 1, they are summed. -1, they are subtracted. And so we have this number of tensors. It looks like a very large number, but optimization algorithms are made for handling such large number of possibilities. And he could use many techniques like constraint programming, set solver, integer programming, meta-risks, many possible meta-risks to find 7 tensors that sum to the correct result. And of course, you don't need to consider all possible tensors. First, you may discard many of them by symmetry, and you may risky restrict the search to a much smaller set of promising tensors. So there are many optimization techniques that can rediscover the Strassen 2x2 algorithm. Okay, and what about 3x3? So the minimum number of multiplications in this case is 23, and it was discovered by Laderman in 1976 by hand. The problem for optimization is more challenging, but why? Because now each tensor has 27 components, so we have larger numbers, about 10 to 12 number of tensors, but yet it's possible to find many alternative solutions with 23 multiplications by set solving and local search, and these have been done since at least 2011. However, this scheme does not improve upon Strassen because the logarithm of 23 in base 3 is 2.854. This is larger than the logarithm of 2 base 7. And so in 2022, we have AlphaTensor. So what is AlphaTensor? So the article was published in Nature. And so the same group that developed AlphaZero, they applied the same state-of-the-art reinforcement learning techniques to AlphaZero. I'm a big fan of chess, so I love AlphaZero. Since 2017, I watched many games played by AlphaZero against Stockfish. So I'm a big fan of AlphaZero. And then they used the techniques in AlphaZero to find the tensors, to improve matrix multiplication. And actually, the same techniques would be applied very soon in AlphaFold, which is a problem that is an algorithm for the protein folding problem, and that was highly successful, led to a breakthrough in biochemistry. and led to a Nobel Prize in chemistry and to Demis Hassabis. But AlphaTensor, the results were more modest, as we see. So first thing, the AlphaTensor was clearly superior to the existing optimization algorithms to the problem. So we could find all the best existing scheming and even improved a few cases. So in the case 4 by 4, it found 47 multiplications. But for a special case, for the case where the elements of the matrix are in the arithmetic field modulo 2. So all the elements are 0 or 1, and they follow the rules of this field known as Z2. Okay, and for the case 5 by 5, it found also improvement. But Z2 is a universe where 1 plus 1 is equal to 0, and this makes easier to find schemes because the undesirable terms that would appear in a matrix can be cancelled, so it's easier. Okay? And so this was AlphaTensor. And now, last week, we have this announcement, this big announcement of AlphaEvolve that could find a procedure to multiply to 4 by 4 using 48 multiplications. And but let's see this. So it improved from 49 to 48. The number of multiplications, but the matrix are assumed to be matrices of complex numbers. Okay? And this improved in Strassen. And why? Because the logarithm of 48 in base 4 is 2.79. So there is an improvement in the exponent of the complexity of the algorithm. But is this a revolution for matrix multiplication as is being announced? In my opinion, no. This is an advance for sure, but it's not a revolution. First thing that if you consider in a pure theoretical view, the 2.79 is very far from 2.37, but okay. Let's consider only the algorithms that are practical, so there is improvement. And the big objection is that the matrix, when the matrix are real valued, which is the most important case, you can treat real numbers as complex numbers, but you have to perform complex arithmetic, which is more costly. So this leads to a larger constant factor that brings an overhead to the algorithm, and it's not clear if the improvement in the exponent is sufficient to compensate for that. So that this will need to be set by experiments. And but I am my area is combinatorial optimization. I recognize that this is a big feat of combinatorial optimization because in this case, the number of tensors is the order of 10 to 22. And finding an improving solution in such a big space is quite remarkable. And the comparison that I used to do with my students is that is like solving a 500 by 500 Sudoku. So the standard Sudoku is 9 to 9, which is, so all Sudokus are easy for computers. But in this case, you have to find a combination of many variables that are exactly that. Okay? And I believe that the classic optimization methods today, they couldn't achieve that. They could have found that solution. So this is a feat of combinatorial optimization. But what's the main point of this talk? And it's claimed in many videos and many even articles and social networks that the new matrix multiplication algorithm is something extraordinary. It can find something that no human mathematician can find. That But let's see if this algorithm is truly so original, so creative. So first, the Strassen algorithm in 1969 is definitely very original because Strassen had to really think outside the box. So at that time, everyone believed that n cubed was unavoidable and he challenged that. Second, he found a completely original way. There were no previous example of how to multiply two matrices using less than n cube product. And moreover, he divided this recursive scheme to leverage this to nn. On the other hand, the new advance is 100% inside the box. So we have known for more than 50 years that it was it was a matter of finding the right tensor combination, of solving this large Sudoku. Okay? And if we may think about this, so the difference of between the two algorithms, and let's compare two algorithms. So this is the heap sort algorithm, and okay, here's the algorithm. There is an idea behind it. There's a logic that can be followed. You can teach this to a student, and this algorithm has loops, has conditions, has recursive calls. Okay, but let's look at the 3 by 3 matrix multiplication that can be found automatically. So even in 2011, it was already found automatically. What is this? So we have a very dual sequence without any meaning of additions and multiplications. So it's different. This is not the. This is what most people think when it's an original algorithm. Okay, and so why this matters? Why this matters? Why, if we consider this new matrix multiplication very original or not? Why this matters? This is a matter of taste, perhaps, but there are some very important impacts. So there's a general public that watches YouTube science channels, and they are believing that artificial intelligence is already outperforming the human mathematicians, and they can devise amazing new algorithms out of nothing. And we have young people, we have teenagers that like mathematics, that love mathematics, and what they conclude by seeing all those videos. One possible conclusion is that okay, human mathematics is finished. So if AI can already find extraordinary matrix multiplication algorithm that no human can find, soon all open math problems will be solved. So better do something else as a profession. And a second conclusion that is quite frequent too is okay, I want to study, but the only topic that is worth studying is AI. So, and this is very bad because even to be a good AI researcher, you need a very solid background in general math and science. So this is quite bad. Okay? But okay, so I'm focusing, I'm talking a lot about matrix multiplication, but this new system, AlphaEvolve, is much more than matrix multiplication. So it solved not only this 4 by 4 matrix multiplication, it solved several other problems in math. So let's have a look. Okay. So AlphaEvolve provided new results, and not only on matrix multiplication, but also in analysis, geometry, and combinatorics. And let's have a look at some of them. For example, here's a problem. We want to pack unit regular hexagons inside a regular hexagon. And we want to minimize the side length of the outer hexagon. So for 11 hexagons, the best construction before used, so the size of this outer hexagon was 3.943, and AlphaEvolve discovered a better configuration that decreased this to 3.931. Okay, and this is the improvement for n equal 12. Okay, nice. Here, what is the problem? We want to locate points in the first case in 2D and the second case in 3D, and we want to locate 16 points in such a way that we want to maximize the ratio of the maximum distance between a pair of points to the minimum distance between a pair of points. And in this first case, the solution was improved from the square root of 12,889. So with a minor improvement, but it's improvement. And here we want to determine how to pack circles of arbitrary radius inside the rectangle, but maximizing the sum of the radii. Okay, so this is another problem where AlphaEvolve improved mathematical result. Here, let's see, what's the kissing? We say that two geometrical objects kiss each other if they touch each other at a single point. And what they call the kissing number is for spheres, it's how many spheres, disjoint spheres, can be packed tangent kissing a given unit sphere. And for 11 dimensions, the best known solution was 592, and AlphaEvolve improved this to 593. Okay? So what all those results have in common? Actually, they were obtained by finding mathematical objects having some very precise described properties and minimizing or maximizing some metric. So all those new theorems or algorithms, from our point of view of optimization, they are improving solutions to some well-known but difficult optimization problems. And this approach is not new. So the computers have been used for that purpose at least since the 1960s. Okay? So there are many examples in mathematics of problems that was framed as optimization problems, and people have used some optimization algorithm, and the result, the best solution found by this algorithm improved some bound or proved some or disproved some conjecture, something like that. But of course, AlphaEvolve done that for several different problems, and no other system have ever done that. But I have to say now about the wonder of AlphaEvolve. There's something really interesting about the way that the system works. So let me try to explain. So it's very impressive first that the system could obtain original results in so many different contexts. But how it works? So the idea is that the user will give a description of the optimization problem, and the description can be, for example, a Python code that will check the solution feasibility and cost. And the user will also give an initial heuristic search code, so a code that looks for tries to solve the optimization problem related to this. And AlphaEvolve will run a loop, and this loop includes large language models that will analyze that code and will try to evolve that code. So the code will be evaluated on some cases, and based on its performance, it will try to propose modifications in the code. Okay, so the code will be modified, and after a number of generations, so the best code will be used to try to find an improving solution. Okay, and the idea is that the code will be optimized for a small class of problems that's trying to solve it, perhaps even for a single instance that is interesting. And so the caveat is that the involved code are also not so original. So actually, the AlphaEvolve makes relatively small changes. So it includes existing algorithm elements from its library that it used the LLM to combine the old algorithm to introduce new elements. And it works a lot by fine-tuning parameters because optimization algorithms have many parameters, and it's really hard to fine-tune those parameters. And this is an overview from the article. So the human will define what is the goal, what wants to be optimized, provides the initial solution. The initial solution is a code, okay? And may provide other knowledge about the problem. And there is a loop that will be run trying to evolve that code to make that code better on solving the optimization problem. Okay, this is quite impressive that this may work. And so what are our conclusions about this? Huh? So why? Who's afraid of AlphaEvolve? So let's see again how AlphaEvolve works. Okay, so AlphaEvolve, there is a loop. Okay, we have the search code, so the initial search code that will be evolved, and there's a loop here. So AlphaEvolve will try to change this code, to tune parameters, to introduce some elements, and this will come from a library of non-optimization algorithms. And eventually, this, if the evolution succeeds, the search code will find the desired new object, mathematical object. Okay, and the new object may be, for example, the packing of circles inside a rectangle. It may be a configuration of spheres in 11 dimensions. This may be a function. This may be an algorithm, as in the case of matrix multiplication, so on. This is a mathematical object. So why people are, say, some people are even freaking out about AlphaEvolve? Because of this. So AlphaEvolve found a new 4x4 matrix multiplication. Okay, but suppose that you believe that this new algorithm is indeed revolutionary, so it will make matrix multiplication much faster in practice. And suppose also that you believe that this new algorithm is a jewel of mathematical creativity. So this closes a loop because this new algorithm will go to the library of non-optimization algorithms. So suppose that the new matrix multiplication is much, much faster. So many optimization codes will run much faster now because they will use the improved matrix multiplication. Okay, and but if AlphaEvolve could find a brilliant original matrix multiplication, why not it will find the new simplex algorithm? Why not we will find something that we cannot even think about this? So this will close a loop because as AlphaEvolve produces fantastic new algorithms, those algorithms go to this library of optimization algorithm and make AlphaEvolve even more powerful, and we have the closed loop. So we have this technological singularity. Okay, and in my view, what is misleading most commentators is that the matrix multiplication algorithm is not so brilliant. It's as brilliant as, in my view, it's as brilliant as this. Okay, this is a feat. Okay, it's very difficult to find the solution, but no one would think that this will will cause the technology, technological singularity. So I don't think no one believes that. But in case of matrix multiplication, there is this misunderstanding that this is a very original algorithm. But this is not a very original algorithm. This is something very new. It's something like this. It's a table of numbers that are summed and multiplied. So there is no, this will not lead nowhere else. Okay. And actually the hype is big. Actually, the hype is really big. So, for example, here we have this very popular YouTube channel, okay, that says that AlphaEvolve grows algorithms and computer code out of nothing. Okay, but this is not true. Okay, what a time to be alive, but this is not true. This is simply not true. Okay. Not yet. We are not close to the technology. So mathematics, as we know, human mathematics will last. Okay? But what's the true impact of AlphaEvolve and mathematics? First thing that very probably will happen that thousands of minor advances similar to those already obtained, so those that corresponding to find some very well-defined objects that are difficult to find by hand will occur in the next years. So probably we will have some bounds of so how many squares can be packed inside the losango of size. So we have many results like this. Okay. I believe that many mathematicians will start to have a system like this as a sidekick to augment the research capabilities, because when you do research in mathematics, so all the time you do some small conjectures, and it would be very good if you have some system that could prove or disprove some of those simple conjectures, so you do not waste time of this. So I think that this will be very frequent that mathematicians are already working with LLMs, but I think that this will be next level. Okay, and I am from optimization. This is my area. And I think that these ideas of AlphaEvolve will have and already had an impact on optimization. So first thing, we have that many optimization algorithms have many parameters, hundreds of them. It's pretty hard to tune those parameters. And AlphaEvolve, there's a loop for tuning parameters, but more than this, because it's possible to produce automatically codes that not only tune parameters, they may hybridize existing approaches, okay? They may mix ideas of one kind of algorithm with another kind of algorithm. We are talking about heuristic algorithms mainly that do local search, that use meta-risk strategies, and those algorithms can be tailored for a very specific case of interest. So instead of having an algorithm that is devised to solve, say, the CVRP, capacitated vehicle routing problem, you may have some super algorithm that is devised to solve the specific routing problem of a particular client. And I think this is something quite promising. So I fully agree that this is something very important. There is a big potential in all those techniques. So this is what I had to say, and thank you for your attention. You can leave your remarks and comments, and try to answer. So bye bye.